Okay, we said the rope stretchers would get a piece of rope and tie 13 knots in it, and they would make a 90-degree angle. And this is where we believe that geometry got its name. Okay. So, geo means earth. Meter means to measure. There's two different ways to spell meter. You can spell it E-R or R-E. And it means to measure. So basically, the exact term, the exact definition for geometry is measuring the earth. So this is where geometry got its name. To measure the earth. It wasn't until much later, in the 6th century BC, that Pythagoras, a Greek mathematician, developed a theorem that showed the same relationship between the legs and the hypotenuse of a right triangle. Archaeology shows that the Egyptians and Babylons became very proficient at measurement and geometric techniques, that the ratio of the circumference of the diameter of a circle is the same for all circles, and that it is slightly more than 3, was known to ancient Egyptians, Babylonian, Indian, and Greek geometers. These techniques were used in their building projects, navigation procedures, and even took a religious significance. Okay, so Pythagoras is a Greek mathematician and he's the one that developed the Pythagorean theorem, and we'll get to that later. But he showed that there's a relationship between the legs of the right triangle and the hypotenuse. Pythagorean theory is a squared plus b squared equals c squared. And it says that the Egyptians and Babylonians became very proficient in the measurement of geometric shapes. So geometry, or geometric techniques. So geometry started with the Egyptians and the Babylonians. I'm going to put a W for with and a line, that's shorthand for with. Egyptians and Babylonians. They're the ones that determined that the ratio of the circumference of it to the diameter of a circle is the same for all circles. It's slightly more than 3. And they could tell this by archaeology. These techniques were used in their building projects, navigation procedures, and even took on religious significance. Oh, I didn't put the year on this, did I? Okay. It says from about 569 to 475 BC. So right over here by Pythagoras, if you could squeeze in here. Can't see that, can you? 569 to 475 BC. You don't have to memorize the date, but I want it there so you can tell time-wise where we're at. Almost 2,000 years later, after the Egyptian rope structures, the Greeks made significant developments in deductive geometry, beginning with Thales and Pythagoras. Thales was able to conclude that the diameter of a circle, the line that connects one end of the circle to the other by going through the center, in other words, this diameter cuts the circle in half. Pythagoras developed the theorem and named it after him, the Pythagorean theorem. Okay. So the Pythagorean theorem was about 624 to 547 BC, so it's in that time frame. In 300 BC, Euclid used the systemizing of deductive logic developed by Aristotle, who was the first to make logic in an abstract form. Okay. So 300 BC, Euclid, E-U-C-L-I-D, and that's a terrible U. Many of the theorems we will investigate later are the result of Euclid's work. Euclid wrote a book called Elements. In this book he compiled abstract ideas such as points, lines, planes, and logically proved theorems involving shapes called triangles, circles, and polygons. Using axioms, a set of definitions, and deductive logic, he began to develop what is known today as Euclidean geometry. So Euclid is the one that you can blame for all the theorems that you're going to learn in this class. Okay, so he developed theorems. He's the one that wrote the book called Elements, and Elements is a whole book of these theorems you're going to learn. This is a book, so I'm going to underline it. I'm going to put it there because Euclid is the author of the book. That's why I put it under Euclid. Okay. 100 or so years later, Archimedes developed the seed ideas for the integral calculus, which was fully developed 2,000 years later by Isaac Newton and Gottfried Wilhelm Leibniz. Archimedes was also instrumental in computing a value for pi, the ratio of the circumference of a circle to the diameter. He determined its calculation was between 3 and 10 over 77 and 3 and 1 over 7. His method was known as the classic method for computing pi. Okay, so about 287 to about 212 BC, Archimedes is the one that he came up with the ideas for integral calculus. So seed ideas means it was the very beginning of it. For integral calculus. Okay, we said geo means earth, meter means measure, so the exact definition for geometry is to measure the earth. In 569 to 475 BC, Pythagoras, a Greek mathematician, he came up with the Pythagorean theorem, a squared plus b squared equals c squared, and that's referring to a triangle. That's why there's only 3 sides. Geometry started with the Egyptians and Babylonians. In 300 BC, Euclid developed theorems, and he wrote a book, Elements, and we're going to learn those theorems. In 287 to 212 BC, Archimedes, he is the one that came up with the seed ideas for integral calculus, and he's also the one responsible for computing a value for pi. Okay. So we're still under Archimedes. I just ran out of room. Gave pi, when you have 2 lines with that squiggly line over it, if you don't know, that's pi, but he gave pi a value. Because we said that the Greeks and Egyptians knew there was a relationship. They knew it was about 3, but it was a little more. Archimedes is the one that actually gave it a value. He determined, he knew that it was between 3 and 10 over 77 and 3 and 1/7. So he knew that the value of pi was going to be right between those 2 numbers. And, alright, after the demise of the Greek civilization, very little was added to the knowledge of geometry until the Renaissance. Okay. In 1637, René Descartes, a French philosopher and mathematician, published a work called Les Géométries. In it, he used algebra to solve problems in geometry. His invention was known as analytic geometry. He was familiar with it. We are familiar with it when we refer to the Cartesian plane, and we'll get to that. And ordered pairs, basically graphing, all that's about graphing. You can blame that on René Descartes. You can blame him for having to graph. We are familiar with it when we refer to the Cartesian plane, the x and y axes, and the ordered pairs. These concepts were invented by taking two number lines and placing them at right angles to one another. He numbered the lines and called 0 the origin. From these beginnings, he was able to develop equations for lines and other geometric figures. Okay. So from 1596 to 1650, and it's not BC anymore, René Descartes he was a French philosopher and mathematician. Philosopher and mathematician. Good enough. He published a work called La Géométries. La Géométries. We're going to underline it. That must be a book. He used algebra to solve problems in geometry. Okay. So his invention is called analytic geometry. So this is analytic geometry. And this is the Cartesian plane. Okay, this includes the Cartesian plane. Okay. At about the same time, and independent of Descartes, Pierre de Fermat, another Frenchman, also created the same thing. What is really unique is that for the first time in history, algebra and geometry were combined. Geometry was now considered a part of algebra and had suddenly become very abstract. Okay. So it says not only Rene, but Pierre, it says, well, about the same time. He was from 1601 to 1665. So it looks like he's about 5 years younger. He created the same thing. So Pierre de Fermat. And I'm gonna put same in parentheses. So you know he created the same thing as Descartes. He discovered the same thing. So algebra and geometry were combined. Algebra and geometry were combined. Okay. In most cases, advances in abstract geometries and mathematics preceded their uses in practical applications and everyday use. But during the Renaissance, it was artists like Leonardo da Vinci and Albrecht Dürer who solicited help from mathematicians to develop a formal explanation of the projective geometry they were using in their artwork. In their artwork, the depiction of people, objects, and scenes were changed and distorted. The artists wanted to know why this was so. The mathematicians Gerard Desargues of Lyons, Blaise Pascal, Jean-Victor Poncelet, a general in Napoleon's army, and Joseph Gourjon made contributions to the development of projective geometry. One should observe that in the case of projective geometry, it was the practical users, the artists, that drove the development of the theoretical abstract geometry by mathematicians. I'm not going to write all those names down. From the time that Euclid wrote his Elements and sometime in the 18th and 19th centuries, mystery and intrigue surrounded one of his essential axioms. Historically, it is known as Euclid's parallel axiom, or the fifth postulate. A mathematician named John Playfair has restated the fifth postulate in this manner. Given a straight line and a point not on the line, only one exact line can be drawn from the point parallel to the given line. The mystic compassing this axiom is this: is it dependent or independent on the other axioms in Euclid's system? If it is dependent, it should be able to be proven to be so. Or can it stand alone, be independent of the others? For 2,300 years, mathematicians tried to prove this axiom dependent, but to no avail. Because of their belief system, it never dawned on them to accept the fact that this axiom was independent. For to do so would mean that there were other geometries besides Euclid's. This would have gone contrary to prevailing beliefs. Very early in the 18th century, a monk by the name of Giovanni Saccheri tried to prove the dilemma by using indirect proof. His results were indefinite and inconclusive, but he was on to something. In denying the postulate, there could be only two other possibilities. First, either no line through the point is parallel to the given line, or second, an infinite number of lines through the point are parallel to a given line. 100 years later, other mathematicians would conclusively resolve the matter. Carl Friedrich Gauss, a German, Janus Bolyai, a Hungarian, and Nikolai Lobachevsky, a Russian, all working independently of one another, invented what is called today the hyperbolic geometry. They created this geometric system by assuming that through a point outside a line, no line through that point is parallel to the given line. Okay, let's see if I can explain this. From 1596 to 1650, René Descartes was a French philosopher and mathematician. He wrote La Géométrie. This is used in algebra to solve problems in geometry. He used algebra to solve problems in geometry. He came up with what is known as analytic geometry, which is the Cartesian plane. And from about the same time, 1601 to 1665, Pierre de Fermat, he discovered the same thing. This was the first time that algebra and geometry were combined. Okay, for the last couple paragraphs that I read, this is what it's saying. Okay, let me interpret this for you. Okay, Euclid wrote a parallel axiom. He said if you have a straight line, okay, here's a straight line. He said if you draw a straight line. Okay, parallel lines, if you remember, parallel lines are two straight lines, and if they go on forever, they'll never ever touch. Okay, they're both exactly straight. He's saying that if you put a point anywhere outside the line, there's only one line that you can draw through this that's going to be parallel to this one. Okay, now obviously we know that that's true, but these mathematicians didn't want to say it was true. I'm not really sure why they didn't want to. It goes against their beliefs. I don't know, but that's what it said. But that's what they're arguing over. A few years later, okay, we said that Giovanni Saccheri tried to prove this using indirect proof. His results were indefinite and inconclusive, but he was on to something. If he denied this, that there was only one line that you could draw here, that means there's only two other possibilities. One is you can't draw a line through this, which is parallel to that. And the other one is that there's several lines that you can draw through that point to make it parallel to that. It's funny how people spend years and years and years on something, and we look at it and we think, well, obviously, seems like common sense to us. Now, 100 years later, Carl Gauss, we just read about him, and James Bolyai, and Nikolai Lobachevsky, and I know I ruined that name, all working independently, invented what is called hyperbolic geometry. And they assumed that they were all trying to prove that no line going through this point is parallel to that one. That's what they're trying to prove. Okay. A few years later, George Frederick Riemann invented elliptical geometry. He created this geometric system by assuming that through a point outside a line, an infinite number of lines are parallel to the given line. That means there's several lines. Now, you can only draw one line through this point that will never ever touch this one, right? So there can only be one line. Okay. George Riemann, now he's trying to prove that there are hundreds. You know, there's just an uncountable number of lines going through that point. These mathematicians had shown that there was more than one geometry. Their creations freed mathematicians from being dependent on the real world and proved more than ever that the abstract nature of mathematics. No longer were axioms self-evident truths. but assumptions believed to be true. It became understood that a mathematical system or geometrical system is made up of 4 elements: undefined terms, postulates, defined terms, and theorems. Okay. I need to write some of this down. Okay. So axioms, we're going to learn a lot of axioms in geometry. We need to learn that axioms are assumptions. They're believed to be true. They're kind of like theories. They're assumptions. Okay. And we said that geometry is made up of 4 elements. Geometry is made up of 4 elements. Undefined terms, postulates, defined terms, and theorems. T-H-E-O-R. This led Bertrand Russell to say mathematics is the subject in which we never know what we're talking about, not whether what we are saying is true. The invention of topography began when mathematician Leonhard Euler in 1735 solved what has become known as a network problem. The problem came to light one day when people of a city in Poland called Königsberg were strolling about town. The Pregel River, which flowed through it, had 2 islands connected by a network of bridges. One bridge connected the 2 islands. The others connected the islands to the opposite shores. One island was connected to shore by 2 bridges on each side, and the other side was connected by 1 bridge on each side. The question that developed from the townspeople was, is there a route that can cross all 7 bridges only once? By developing a network, Euler was able to prove that it was not possible. Later, Gauss observed that figures had properties of form that were much more abstract than geometry. A student of his named Augustus Mobius worked in the area he named topographical transformation. He recognized that shapes could be sketched, shrunk, twisted, bent, or folded and still maintain certain invariant properties. The famous Mobius band was, of course, named after him. Riemann contributed to further advancement in topography by studying surface properties. Henry Poincare developed algebraic topography near the turn of the 20th century. Okay, we went through a lot of information there. I want you to study your notes and go ahead and answer the questions.